When determining the appropriate amperage for a voltage drop calculation related to a motor, you should use the motor full load current, or FLC, as indicated on the motor nameplate. The table values from the electrical code are not appropriate for this specific calculation. The 125% factor is not directly applied to the wire size calculation itself. Instead, it's used to adjust the calculated circular mils to account for the additional current that the conductor may carry under abnormal operating conditions, such as during starting or short-term overloads. The adjusted circular mil value is calculated by multiplying the initially calculated circular mils by 1.25. Let's walk through an example calculation. Assume a single-phase, 5 horsepower motor operating at 115 volts. The motor nameplate indicates a full load current of 52 amps. The distance from the power source to the motor is 110 feet, and we want to limit the voltage drop to 3%, which equals 3.45 volts. The K factor, which is a constant for copper wire, is 12.9. Firstly, calculate the circular mils using the voltage drop formula for a single-phase circuit, which is circular mils equals 2 times K times I times D divided by the voltage drop, where K equals 12.9, I equals the motor full load current of 52 amps, D equals the distance of 110 feet, and the voltage drop equals 3.45 volts. Plugging in these values, we get circular mils equals 2 times 12.9 times 52 times 110 divided by 3.45, which equals approximately 485,370 circular mils. Secondly, adjust the circular mils value for the 125% load factor. This is done by multiplying the initial circular mils value by 1.25. So, the adjusted circular mils equals 485,370 times 1.25, which equals 606,713 circular mils. Thirdly, select the appropriate wire size. Using a wire table, you need to find the wire size with the circular mils value closest to or greater than 606,713. In this case, a number 2 American wire gauge, or AWG wire, would be appropriate. It's important to note that the electrical code does not provide specific guidance on using the motor nameplate current versus table values for voltage drop calculations. However, using the motor nameplate current is generally preferred because it represents the actual operating condition of the motor. Applying the 125% factor to the conductors when sizing the wire involves a nuanced understanding. It's not directly applied to the wire size calculation in the voltage drop formula. Instead, it's used to adjust the calculated circular mils value, accounting for potential additional current under certain operating scenarios like motor starting or short-term overloads. The electrical code section 430.22 indeed directs to size the conductors at 125% of the motor's full load current to accommodate such scenarios. This percentage isn't factored into the voltage drop formula, but rather ensures that the conductors can safely handle the increased current demand during motor startup or temporary overloads, preventing overheating and potential damage. The voltage drop formula, as correctly stated, is circular mils equals 2 times K times I times D divided by voltage drop. In this formula, I represents the motor's full load amperage, or FLA, obtained from the motor's nameplate, not from the electrical code tables. The electrical code tables are used for different purposes, such as determining the ampacity of conductors based on insulation type and temperature rating. The motor nameplate value provides a more accurate reflection of the motor's actual operating current under normal conditions. After calculating the circular mils using the voltage drop formula and the motor's full load amperage, you adjust the result by the 125% factor to obtain an adjusted circular mils value. This adjusted value is then used to select the appropriate wire size from the wire tables. To recap, the formula is used to find the circular mils required to meet the voltage drop requirement. Then the result is increased by 25% to ensure adequate capacity for the conductor based on code requirements. The discrepancy encountered arises from the two distinct purposes of these calculations: voltage drop and conductor ampacity. Voltage drop calculations are aimed at ensuring efficient motor operation and preventing performance issues due to excessive voltage drop. Conductor ampacity calculations, on the other hand, focus on safety, ensuring that the conductors can safely carry the anticipated current without overheating or posing a fire hazard. The 125% factor is specifically related to conductor ampacity and is mandated by the electrical code to enhance safety margins, especially considering the potential for motor overload or high inrush currents during startup. Firstly, determine the motor's full load amperage from the motor nameplate, not from the electrical code tables. Secondly, calculate the required circular mils using the voltage drop formula. Circular mils equals 2 times K times I times D divided by voltage drop, using the motor's full load amperage from the nameplate. Thirdly, adjust the calculated circular mils by the 125% factor. Circular mils adjusted equals circular mils calculated times 1.25 to account for conductor ampacity requirements. Fourthly, select the appropriate wire size from the wire tables based on the adjusted circular mils value. Remember, voltage drop calculations focus on motor performance and efficiency, while conductor ampacity calculations prioritize safety and compliance with the electrical code. Using the motor nameplate amperage and applying the 125% factor appropriately ensures both efficient motor operation and safe conductor sizing. The confusion often arises from the separate requirements for voltage drop and conductor ampacity, each serving a distinct purpose in electrical system design. Voltage drop calculations aim to ensure that the voltage at the motor terminals remains within acceptable limits, typically no more than 3% voltage drop for branch circuits and 5% overall. This ensures that the motor operates efficiently and delivers its rated performance. Conductor ampacity calculations, on the other hand, are focused on selecting conductors that can safely carry the anticipated current without overheating or posing a fire hazard. The electrical code mandates that conductors be sized at 125% of the motor's full load current to provide an additional safety margin, especially considering the potential for motor overload or high inrush currents during startup. The voltage drop formula involves several variables, including K, which represents the direct current resistance for a 1 circular millifoot of conductor material, I, which represents the current flowing through the conductor, D, which represents the one-way length of the circuit, and voltage drop, which represents the maximum allowable voltage drop in the circuit. By plugging in the appropriate values into this formula, you can determine the minimum circular mil area required to limit voltage drop to the specified level. After calculating the circular mils required to meet the voltage drop requirement, you then adjust this value by the 125% factor to ensure that the conductors can safely carry the anticipated current, taking into account potential overload or high inrush conditions. It is crucial to consult the electrical code and relevant wire tables to ensure that the selected wire size meets both the voltage drop and ampacity requirements. Additionally, factors such as ambient temperature, conductor insulation type, and conduit fill should be considered when selecting the appropriate wire size. Voltage drop is influenced by several factors, including the length of the circuit, the current flowing through the conductor material and size, and the power factor of the load. Longer circuits, higher currents, and smaller conductors will result in greater voltage drop. Similarly, loads with lower power factors, such as inductive loads like motors, will also contribute to increased voltage drop. To minimize voltage drop, it's essential to use appropriately sized conductors, shorten circuit lengths whenever possible, and improve the power factor of the load through the use of power factor correction capacitors. The electrical code provides guidance on acceptable voltage drop limits for various types of circuits, including branch circuits, feeders, and service conductors. Adhering to these limits is crucial for ensuring efficient equipment operation and preventing performance issues due to excessive voltage drop. Understanding the principles of voltage drop and conductor ampacity is essential for electrical engineers and electricians to design and install safe and efficient electrical systems. By carefully considering all relevant factors and following the guidelines provided in the electrical code, it's possible to ensure that electrical systems operate reliably and safely for years to come. The 125% factor, as specified in the electrical code, is primarily intended to address the conductor ampacity requirements, ensuring that the conductors can safely carry the anticipated current, including any potential overload or high inrush conditions. This factor is not directly incorporated into the voltage drop calculation, as voltage drop is primarily concerned with ensuring efficient motor operation and preventing performance issues due to excessive voltage drop. To determine the appropriate wire size for a motor circuit, it's essential to perform both voltage drop and ampacity calculations, taking into account all relevant factors, such as motor full load current, circuit length, conductor material and size, ambient temperature, and conductor insulation type. The wire size should be selected to meet both the voltage drop and ampacity requirements, ensuring both efficient motor operation and safe conductor sizing. In cases where the voltage drop calculation results in a larger wire size than the ampacity calculation, the larger wire size should be selected to meet both requirements. Conversely, if the ampacity calculation results in a larger wire size than the voltage drop calculation, the larger wire size should be selected to ensure safe conductor sizing. It's important to note that the electrical code provides specific guidance on conductor ampacity ratings based on conductor size, insulation type, and ambient temperature. These ampacity ratings should be consulted when selecting the appropriate wire size for a motor circuit. Additionally, factors such as conduit fill and dirting factors for multiple conductors in a raceway should be considered to ensure that the selected wire size can safely carry the anticipated current. A motor operating at 115 volts with a nameplate full load amperage of 52 amps, located 110 feet away from the power source, requires careful consideration of voltage drop and conductor ampacity to ensure efficient and safe operation. The voltage drop formula, circular mils equals 2 times K times I times D divided by voltage drop, is used to determine the minimum circular mil area required to limit voltage drop to the specified level. In this case, assuming a maximum voltage drop of 3%, which equals 3.45 volts, the required circular mils can be calculated as follows: circular mils equals 2 times 12.9 times 52 times 110 divided by 3.45, which equals approximately 485,370 circular mils. To account for conductor ampacity requirements, the calculated circular mils value is adjusted by the 125% factor. Circular mils adjusted equals circular mils calculated times 1.25. This results in an adjusted circular mils value of 606,713 circular mils. Based on wire tables, the number 2 American wire gauge conductor has a circular mil area of approximately 66,360 circular mils, which is sufficient to meet the calculated circular mils adjusted value. However, it's essential to verify that the number 2 American wire gauge conductor also meets the ampacity requirements for the motor circuit. According to electrical code tables, a number 2 American wire gauge copper conductor with THHN insulation has an ampacity rating of 95 amps at 75 degrees Celsius. This is more than sufficient to carry the motor's full load current of 52 amps, even when considering the 125% factor. Therefore, a number 2 American wire gauge copper conductor with THHN insulation would be an appropriate choice for this motor circuit, meeting both the voltage drop and ampacity requirements. It's important to note that this calculation assumes that the ambient temperature is within acceptable limits and that there are no other factors that would require dirting the conductor ampacity. Additionally, the electrical code should be consulted to ensure compliance with all applicable requirements. The 125% factor is not directly applied to the voltage drop calculation, but rather is used to adjust the calculated circular mils value to account for conductor ampacity requirement. The 125% factor ensures that the conductors can safely carry the anticipated current, including any potential overload or high inrush conditions. A confusion arises from the fact that voltage drop and ampacity are two separate considerations that must be addressed when sizing conductors for a motor circuit. Voltage drop is primarily concerned with ensuring efficient motor operation and preventing performance issues due to excessive voltage drop, while ampacity is primarily concerned with ensuring that the conductors can safely carry the anticipated current without overheating or posing a fire hazard. The electrical code addresses both voltage drop and ampacity requirements separately, providing guidance on acceptable voltage drop limits and conductor ampacity ratings based on conductor size, insulation type, and ambient temperature. By carefully considering both voltage drop and ampacity requirements and following the guidelines provided in the electrical code, it's possible to select the appropriate wire size for a motor circuit, ensuring both efficient motor operation and safe conductor sizing. The selection of the appropriate wire size for a motor circuit requires careful consideration of both voltage drop and conductor ampacity, taking into account all relevant factors such as motor full load current, circuit length, conductor material and size, ambient temperature, and conductor insulation type. The voltage drop calculation involves determining the minimum circular mil area required to limit voltage drop to the specified level, while the ampacity calculation involves selecting conductors that can safely carry the anticipated current, including any potential overload or high inrush conditions. The electrical code provides guidance on acceptable voltage drop limits and conductor ampacity ratings, and these guidelines should be followed to ensure both efficient motor operation and safe conductor sizing. The 125% factor is applied to the motor's full load current to determine the minimum conductor ampacity required, while the voltage drop calculation is performed separately to ensure that the voltage at the motor terminals remains within acceptable limits. The selected wire size should meet both the voltage drop and ampacity requirements, and in cases where the voltage drop calculation results in a larger wire size than the ampacity calculation, a larger wire size should be selected to meet both requirements. Conversely, if the ampacity calculation results in a larger wire size than the voltage drop calculation, the larger wire size should be selected to ensure safe conductor sizing. The 125% factor is applied to the motor's full load current to determine the minimum conductor ampacity required, while the voltage drop calculation is performed separately to ensure that the voltage at the motor terminals remains within acceptable limits. The selected wire size should meet both the voltage drop and ampacity requirements, and in cases where the voltage drop calculation results in a larger wire size than the ampacity calculation, the larger wire size should be selected to meet both requirements. Conversely, if the ampacity calculation results in a larger wire size than the voltage drop calculation, the larger wire size should be selected to ensure safe conductor sizing. Understanding the distinction between voltage drop and ampacity requirements and following the guidelines provided in the electrical code is essential for selecting the appropriate wire size for a motor circuit, ensuring both efficient motor operation and safe conductor sizing. The appropriate wire size for a 115-volt, 5-horsepower motor with a nameplate full load amperage of 52 amps, located 110 feet away from the power source, requires a careful assessment of voltage drop and conductor ampacity. The voltage drop formula, expressed as circular mils equals 2 times K times I times D divided by voltage drop, helps determine the necessary circular mil area to maintain voltage drop within acceptable limits. Assuming a maximum voltage drop of 3%, equivalent to 3.45 volts, the calculated circular mils would be approximately 485,370. Adjusting this value by the 125% factor for conductor ampacity results in an adjusted circular mils of 606,713. Consulting wire tables, a number 2 American wire gauge conductor with a circular mil area of roughly 66,360 circular mils appears adequate. However, confirming its ampacity rating is crucial. Typically, a number 2 American wire gauge copper conductor with THHN insulation boasts an ampacity of 95 amps at 75 degrees Celsius, surpassing the motor's full load current of 52 amps, even after accounting for the 125% factor. Therefore, a number 2 American wire gauge copper conductor with THHN insulation seems suitable for this motor circuit, satisfying both voltage drop and ampacity criteria. It's imperative to ensure that ambient temperature remains within permissible limits and that no other factors necessitate conductor ampacity rating. Moreover, adhering to all relevant electrical code requirements is paramount. In summary, the selection of wire size involves distinct calculations for voltage drop and conductor ampacity. Voltage drop calculations ensure efficient motor performance by limiting voltage drop to acceptable levels, while ampacity calculations guarantee safe conductor operation by accommodating potential overloads or high inrush currents. The 125% factor plays a pivotal role in conductor ampacity as mandated by electrical codes to enhance safety margins. Discrepancies between these calculations arise from their separate objectives, voltage drop focusing on motor performance and ampacity prioritizing safety. Employing the motor nameplate amperage and appropriately applying the 125% factor ensures both efficient motor operation and safe conductor sizing, thereby mitigating confusion and optimizing electrical system design.